Hi guys, in this video we're doing linear programming exam revision. So let's look at our first equation. So first question says shade in the visible region visible in the graph for the following constraints if one exists. Otherwise write no visible region across the graph to save your time. The constraint lines have already been drawn in. So since you already have a graph and then you also have the constraint, so what you have to do is to shade the visible region if it's there, and then if it's not there, then just write no visible region. Then let's look at this. So first thing to do when you're given this question, you have to identify the origin of the graph. So the origin is this. We have a 0 here and then 0 there. So this is the origin. Then this is the y-axis, that's the x-axis. So after identifying the x-axis and then the y-axis, then to identify the slopes of the graphs. So this one here is a positive slope, and then this graph here is a negative slope. So therefore, this first constraint here correspond to this one here, and then the second constraint, this correspond to the other line because it has a positive gradient. Just look to the x1 is positive, therefore the gradient is positive. So if the x1 is negative, the gradient is negative. Then after identifying the slopes, then the next thing to do, since they told you that you don't have to waste your time, so don't even do the thing of dotting. That's a waste of time. What you have to do here is just look at this and then choose any point here, choose any point there, choose any point here, choose any point here. So the point that satisfies the both constraint, shade that area. So if there's no point that satisfies the both constraint, and then write no visible region. So let's take this point here. Let's make a point here. So this point here is going to be -1 and then 1 and 0. So our x2 is equals to -1. I took it from here, and then our x1 is equals to 0 is this one here. So then after that, for the first constraint, therefore the x1, this is going to be 0, and then that's -1. So therefore that means -1 is not great. This is going to be, answer is going to be 1, then 1 is greater than or equals to 3, which is not true, and then leave that point. Then go to the next one. So let's choose a point here. A point here can be -3 and -2. So the point here is -3, -2. Then our point is x2 is equals to -3. Then x1 is equals to -2. Remember, if one constraint fails and then move on, don't check the other one. Then here we're testing the first constraint. So the first constraint is going to be the first constraint now is going to be x1 is -2, and then -2 times -1 is going to be 2, and then -3 times -1 is going to be plus 3, and then 5 is greater than 5 is greater than or equals to is greater than, not equals to, is greater than 3, and then check the second one. So the second one is -2, then what's 3 -3 times -1 is going to be plus 3, then it's less than or equals to 3. Oh, it's less than 3. Then this and that is 1, and then 1 is less than 3. So therefore we take this one here. So after that, if you got that, if you got that, then you have to shade that area. So now what you have to do, shade this area. So this is our visible region. So this is the visible region, because all the points here in this region will satisfy the constraint. Then you are done. That's the visible region. So that's your visible region. Then let's move on to the next question. So we have another one, is the very same question, but this one is a little bit trick. Then they say shade in the visible region visible in the graph for the following constraints if one exists. Otherwise, write no visible region across the graph to save your time. The constraint lines have already been drawn in the graph. So here I already told you the procedure. The first thing to do is to identify the origin. So our origin here, we have 0 and 0 here. This is our origin. So there's no need to identify it because it's here. Then after that, what you have to do, we have to look at these two constraints. So we have x1 is less than or equals to 3. So 3 is this. Then if they say less than or equals to, therefore they're referring to the whole of this area here. They're referring of the whole of this area here. And then let's move on to the second one. It says x2 is greater than or equals to 3. So x2 is this, then is greater than or equals to 3. So they're referring to this area here, to this portion. And then the last one, the first one actually, this one, then we'll move on to the first one. It says x1 plus x2 is greater than or equals to. So they're referring to the slope that it's greater than. So is this one here. So is this one. So here we have only one area that satisfies all the colors. If you can check this area here, if you can check that area, all the colors are there. The blue is there, black is there, and then also the red is there. Then that area, therefore, is the visible region. Then we have to shade that area in here, or to make sure that area, that this is the correct one. Therefore, you can choose any point here to check whether the point in this area will satisfy all the constraints. So to make things easier, let's choose this point here. This point here is 3.5 and then 1.5. So x2 is equals to 3.5 and then x1 is equals to 1.5. So we're doing the first one is going to be 1.5 plus 3.5, which is going to be greater than 3.1. So satisfy the first one. The second one is x1. So x1 is this. x1, which is 1.5, must be less than 3, which satisfy that. Then the x2 is 3.5, which must be greater than 3, which is true. So all of them are satisfied. So you can choose which way is simple for you, is the one of choosing the points or the one of shading. So if you find the shading as a simple one, choose the shading. Then if you want to choose the points and then substitute, you can choose the points and then substitute. Then let's move on to the next question. These are the long questions. Consider the following optimal table for a maximization. This is a maximization linear programming problem. Then give the optimal solution from this table. So they're saying that give the optimal solution from the table, not to compute the table, just give that means you have to take the optimal solution from the table and then give them. So what you have to be familiar with here is to how to read the solution from the table. So here, how many variables do we have? We have x1, x2, x3, x4, x5. We have 5 variables. So since we have 5 variables, then our solution is B. So here you have to know that which variables are the surplus variables or slack variables. Then the surplus variable or slack variables are what we call a basic variables at the initial table, because even if it's not an initial table, but when you are doing the problem, they are going to be the basic variables. And then the non-basic variables are the variables that have a coefficient of non-zero on the objective function. So here you have xt. Xt means the x transpose is equals to open bracket. You just read from your table. So here, from here, if you can look, our solution here is 9 multiplied by 1 over 9 and then 5 over 9. So if you can read the solution here, so this is the solution. So if this is the solution, the x1 is not there. That means the x1 doesn't have a solution. Sorry, x1 is there. The x2 is not there. That means the x2 doesn't have a solution. x3 is not there. That means doesn't have a solution. x5 is not there. That means doesn't have a solution. So x1, we're reading from there, is 5 over 9. And then our x2 is 0 since it's not there. And then x3 is 0 since it's not here. And then our x4 is there. It's 9 to 1 over 9. And then our x5 is 0 since it's not there. This is the solution for the x. And then for the z, z is equals to 50. Then you're done. That's your solution. So this is the optimal solution from the table. You just take it from the table. Then you have a b. Determine the alternative solution using the following table. So since here, this table here, if you can look at x2 have a 0 coefficient, and then the other in the other constraints it doesn't have a 0. And then as I told you, we're going to look at the basic variables and then the non-basic variables. So a basic variable is a variable that has a coefficient of positive 1 in one constraint, and then the coefficient of zeros in the other constraints. And then we have x2, which have a coefficient, and then the basic variables actually, they have a 0 coefficient on the objective function. All of them, they have a 0 coefficients on the objective function. So we have x2 here, which have a 0 also on the objective function, but it's not the basic variable. Why? Because it doesn't have a 0 here, and then also there's not 0. So our x2 is not classified as a basic variable. It's non-basic variable. But since we have this x2 that is 0 there, so our z is going to be 0x1 plus 0x2 plus x3 plus 0x4 plus 10x5. So x5 is a non-basic variable, x3 is a non-basic variable, and then x2 is a non-basic variable. And then our basic variables are x1, and then x4. x1 and then x4. So if I decide to bring to bring x1 to the basis, like if I say x1 is 1, so if x1 is 1, it's 1, there's no change on the z. The z will remain the same because the coefficient of x1 doesn't change. If I say x2, it's 1 now, I bring it to the basis, there's no change into the objective function because x2, the coefficient of x2 is 0. And then if I say x4, it's 1 now on the basis, there's no change on z because the coefficient of x4 is 0. But if you can bring on x5 or x3, there will be a change on the z. So remember that x2 is not a basic variable, it's a non-basic variable. So bringing x2 on the basis, there's no change. Then if there's no change, that means we are finding the alternative solution with no change in z. So the z remain the same, that solution will remain the same. If it's 50, will remain as 50, but these are going to change. These values, they are going to change. So to do that, we are going to bring x2 to the basis. We are bringing the one that is non-basic variable, and then at the same time it doesn't make any change to the objective function. So that's what you should bring. If there's a one variable that's a non-basic variable, and then when you bring that variable to the basis, it doesn't cause any change to the objective function, therefore you have alternative solution. So to do that, therefore x2 has to enter, and then if it enters, we're going to do the ratio here. We're going to do the ratio operation. Then to do the ratio calculation, let's extend our graph. Then we're going to say, since this x2 is chosen to be on the basis, we're bringing x2 to the basis because we'll cause no change on the z. Therefore that's an alternative solution. Then therefore we're going to take this number, this 9 here, we divide it by this, we get a negative, and then just write a dash. We don't take a negative, and then take this 5/9 divide by 1/9. So 5/9 dividing by 1/9, you will get 5. You will get 5. So this, and then therefore choose the pivot element. Then the pivot element is going to be this one here. This is this 1/9 here. So this 1/9 is pivot element. Then after getting that pivot element, therefore you have to reduce the pivot element to 1. You have to get 1 here, and then here you have to get 0. Here you have to get 0. So already there you already achieved 0 here. So there will be no change on the first line. So the first line, since you have to achieve 0 here, what was here you have to get 1, and then here 0, and then there's 0. So you already have 0 on the first row. So that means there's no change on the first row. You're going to copy it the way it is. So z is 1, x1 is still going to be 0, x2 is 0, and then x1, x3 is 1, x4 0, x5 10, then b is 50. So do you see that the b is still 50? There's no change on b, because you already achieved 0, what you were supposed to. So here you have to change this 4 multiplied by 7/9 to 0. So to do that, you're going to do this row operation. You're going to say this R2 will turn to R2 plus, since this is minus, and then say plus. Or if you just want to be polite enough, you can say minus, open bracket, into minus, minus, you take this one here, you take this number here to the denominator 1/9, and then you take 4 multiplied by 7/9 to the numerator. This is your coefficient, and then you multiply that by the R3. Okay, here then for the second constraint is R2 plus 43 R3. Then to do the row operation, you say for this one, for the first one here is 0, then plus 43 multiplied by our R3, it's 1, then the answer is 43. Then here, therefore you're going to have 43. Then you write 43 here. Then 43, we'll move on to the next one. So you still have R2 plus 43 R3. Then for this one is going to be minus 4 times 7/9. Then plus 43 times 1/9. Then this, remember, we're going to be careful of this number here, because we have to say 4 times 9 plus 7. 4 times 9 plus 7, which we're going to get minus 33. Then plus minus 33 over 9. And then this one here is going to be 43 times 1 over 9, which is 43 over 9. Then the answer is 0. Then you write 0 for the second one iteration. Then you are going to do the very same thing for the rest of the row. Then for the next row, this is 0 here. For the next row, after operation, you are going to get 37 over 9. The next, it's 1. Next one is 5. Next is 33. Then for the last row, since we should achieve 1 here on 1 over 9, so to get 1 on 1 over 9, you can divide this by 1 over 9, or you can multiply by 9 to get 1. So to get 1 here, you have to multiply this by 9 or divide by 1 over 9. Then the whole row, remember, we don't do on one element only for the whole row. Then row 3 is going to turn to row 3 multiplied by 9. Then here you have a 0 times 9 is 0. They already gave you as a 0. And then 1 times 9 is 9. Then 1 over 9 times 9 is 1. We achieved that one. Then minus 5 over 9 times 9 is minus 5. Then 0 times 9 is 0. 1 over 9 times 9 is 1. 5 over 9 times 9 it's 5. Then this is your new table. So since it is such, you have to identify to find the alternative solution. So we had a non-basic variable that have a 0 coefficient on the objective function. That's why we have an alternative solution. So this is the alternative solution. So to check that it's an alternative solution, check the value of b. If you did the row operation correctly, the value of b have to stay the same, doesn't have to change, because that's not the another optimal solution. It's the very solution, but it's an alternative. So the value of b have to remain the same. So initially our b was 50, and then now our b is 50. So therefore we have alternative solution. The solution remain the same, but the constraints changes. So here, since after doing this, we brought x2 to the basis. Then if x2 was to the basis, now we have to fill this space here. After doing the row operation, you have to fill the space here. You have to choose which one is the entering variable and then which one is the leaving variable. So we have x2 as the entering variable. x2 enters. Why? Because x2 is the non-basic variable that have a coefficient of 0 on the objective function. So bringing x2 to the basis has no change on the objective function. Then x2 enters. Then we should choose the one that it's leaving. So since the ratio, the smallest ratio is here. The smallest ratio is here. This is the smallest ratio here, because there we got 5. This is 5, yes, negative. This is r. Then you're going to look at this x1 and then x4. The one that it's not 0 on this row is the one that leaves. The one that's not 0 on this row is the one that leaves. So our x4, you are looking to the basic variables. Our x4 here is 0, and then our x1 is 1. So therefore the x1 is the one that it's supposed to leave, because as a coefficient of 1 on that row. So you are looking to the basic variables after identifying the pivot column. So this is the pivot column, and then you identify also the pivot row, and then after that look for the basic variable that has a coefficient of 1 on that row, so it's x2. Therefore it's x1 is leaving, x1 leaves. So if x1 leaves and then x2 enters, where it was x1, we're going to replace it with x2. So therefore here I'm going to write x2. I'm replacing x1 with x2 because x1 is leaving while x2 enters. Then for x4, it doesn't change. The position is still x4. So this is your new solution. So the solution is xt is equals to, open bracket, reading from this, we have a x1 here. x1 is 0 because it's not there on the basis. Then x2 now it's 5. Reading from here, it's 5. Then your x3, since it's not there on the basis, is 0. x4 is there, is 33. And then the x5 is not there, is 0. So this is the alternative solution. So these two solutions are not the same, but they lead to the very same z. So it's either use this optimal solution or use that one. Your value of the value of z is going to stay the same. It's going to be 50. You can substitute your variables as this ones here or this, but the value of z doesn't change. Then this is how we deal with alternative solution. Then now I'm moving on to the next question. So the next question says, circle the pivot element of the following table for maximization problem. So the problem is a maximization, it's not a minimization. So first thing to do if you want to identify the pivot element is to look for the highest negative number or the smallest number that has a negative sign. So this is the highest negative number. Then circle this column here. Then after circling that column, do the ratio operation. To do the ratio operation, you can extend your table and then say this is R, then say 0.2 divided by negative 1.6. So if you get a negative, write a dash. We don't deal with the negatives. The second thing to do is say 5 divided by 1 and then you get 5. Then 5 is going to be the smallest ratio. So if 5 is the smallest ratio, therefore this is the pivot row. Then you are going to do this. So you look where these two things meet, the pivot column and then the pivot row. So they meet here and then circle this number, and then that number, it's your pivot element. So since they just said you have to circle that pivot element, just circle this, so pivot element. Then let's move on to the next question. So next question again says, circle the pivot element of the following table for maximization problem. Still maximization. So we're looking for the highest negative. Highest negative here is this. Then do that to that pivot column. Then do the ratio. So this one is 7 divided by minus 10, which is negative. Then this is 5 divided by 10, which is 1 over 2. Then this is 3 divided by 10, which is 3 over 10. So here you look for the smallest number. So here the smallest number is this one, is 3 over 10. 1 over 2 is greater than 3 over 5. Then do this. Then after that, do this. So this is your pivot row. This is your pivot column. Then after that, where these two things meet, it's your pivot element. So your pivot element in this case, it's this 10 here, it's 10. So just circle this 10. That's your pivot element. Question. It says, consider the following LP problem. This is a maximization. Max Z is equals to minus 9x1 plus 5x2 plus 2x3. Subject to minus 2x1 minus 6x2 plus 7x3 is less than or equals to 8. Minus x1 minus 6x2 plus 3x3 is less than 10. x1, x2, x3 is greater than or equals to 0. So here the problem is in a correct form because we don't have any problem, any constraint that has a negative sign on the left, a number that is negative on the right, sorry, or any variable that is unrestricted. All the variables are restricted. Then they say complete the initial simplex table. So this is the initial one. So the first thing that you have to do here, you can write this problem in a standard form. So to write this problem in a standard form, you're going to do what we did last. You just max z is equals to minus 9 x1 plus 5 x2 plus 2 x3, and then subject to minus 2 x1 plus minus 6 x2 plus 7 x3. So here, since this is less than, you have to add the slack variable. So we add the slack variable, let's call it x4. x4 is equals to 8. Then for the next one, or let's call it s1 as they did here, because if we can call it s4 it's going to cause a confusion. Let's call it s1 is equals to 8. So for the second constraint is minus x1 minus 6x2 plus 3x3 plus s2 is equals to 10. Then restrict all of them, don't forget x1, x2, x3, s1, s2 are all greater than or equals to 0. Then here on your objective function, after writing the constraints in a standard form, you can come and add 0 s1 plus 0 s2. So this row here is the objective function. So the objective function z is 1. So objective function, remember that the z is equals to minus 9x1 plus 5x2 plus 2x3. So to get the value of b, just take everything on the right hand side to the left hand side. So if you take this to the left hand side, 9 minus 9 is going to be positive 9. This is going to be negative, that's going to be negative. So that you can get z minus something is equals to 0. Is equals to 0. So this value here, the b, is going to be 0. The b here initially is 0. So since its initial b is 0, then x1, if you take this to the other side, therefore 9 change the sign. The coefficient of x1 is going to be 9 now. The coefficient of x2 is going to be minus 5. The coefficient of x3 is minus 2. s1 is 0, s2 is 0. And then the second line here, this space here, it's for is for basic variables here. You write the basic variables. So basic variables, as I told you, are the variables that have a 0 coefficient on the objective function, and then the coefficient of positive 1 or minus positive 1 on the other constraints, on one of the constraints, sorry. So we have s1. The s1 is one of the basic variable because s1 have a coefficient of 0 here, and then 1 here, and then 0 there, and then also 0 on the second constraint. So s1 and s2 are basic variables. So this space here, it's for them. Here you write s1, here you write s2. Then after that, here is the coefficients on the first constraint of each variable. So the coefficient on the first constraint of the x1 is this, it's minus 2. You write minus 2 here. For the second constraint, it's minus 6. You write minus 6. The following one, it's 7, and then 1, and then 0. then 0, and then this is 8 here. Here this is 8, it's the solution. So this is 8. Let's see this one. These values here are the values of b. So this is 8 from there. That's the value of b. Then the last constraint, you have a coefficient of x1 as -1, x2 as -6, x3 as 3, and then s1 in this constraint here is 0, and then s2 is 1, and then the value of that is 10. So you are done with this question. You completed the table. Then now let's move on to the next question. So we have this question here. Say, consider the following table for maximization linear programming problem. Determine the next table. So it's still the very same question here. Consider the following table for maximization linear programming problem. Determine the next table. So you do the very same thing. So this is the initial table. This is the initial table. So now I have to identify the next table. So what you have to do first is to check out is the maximization problem or minimization. So this is the maximization problem. So we're going to look first for the coefficient, the variable that has highest negative coefficient on the objective function, which in this case is x2. x2 as a -4, which is the highest negative number in the objective function. Then after that, do the ratio. So the ratio here are, this is going to be the h here because 3 divided by -5 is negative. Then we don't take a negatives. Then you are going to get 4 minus divided by 2, which is 2 for this. Then therefore, we are going to consider this one as the smallest ratio. So if that's the smallest ratio, then you are going to do this. When these two things meet, the pivot column and then the pivot row, call that number the pivot element. So our pivot element here in this case is 2. So what you have to achieve is to make 2 1. To make this 2 1, and then make this -5 0, then make this -4 0. So to do that, since you have a 2 here, you're going to say for the row 1 will turn to row 1, and then minus open bracket, you take this 2, you take this 4 here, it's going to be -4, you divide by 2 to get a multiplier, and then after that you multiply it by the first this row here, the second row, because second row is the pivot row. Then for the last one, you are going to say R3 will turn to R3 minus open bracket, that's -5, divide by 2, you multiply it by R2, that's the major row, the pivot row. Then after that, you do the row operation. We're going to fill our table. But before, you have to identify again the entering variable and then the leaving variable. So since x2 is on the pivot column, so therefore x2 enters. The variable on the pivot column enters. Then you look for the basic variable that's on this, on the pivot row. That's on the pivot row. Here, this is your pivot row. Then you look for the basic variable. The basic variable, remember that the variables that are here. So those variables are x4 and then x5. For the x4 and x5, look for the one that have a coefficient here of 1. So in this case, x4, its coefficient is 1. So therefore, x4 is going to leave because it has a coefficient of 1 on the pivot row. So x4 leaves. So if x4 leaves and then x2 2 enters. So the position of x4 is going to be replaced by x2. So here is x2. Remember this position was for x4, then it's replaced by x2 now. So next thing to do, x5 remains on the same position. So here you just do the row operation according to these algorithms here. Then you have to fill the row 1 using this algorithm, and then also row 3 using this algorithm. Remember, we have to achieve 1 here. Sorry, I forgot. We have to achieve 1 here. So to achieve 1, you just say 2 divided by 1. So 2 divided by 1 multiplied by row, not 2 divided by 1, sorry. 2 divided by 2 multiplied by row 2. So this row 2, you just say 2 divided by 2. Or you can say, the simplest way, you just say row 2 divide by 2. You're going to divide each and every element on row 2 by 2, so that you can get 1 here. Because if you divide 2 by 2, you'll get 1. So to achieve 1 here, you should divide each and every element on this row by 2. You start with this one here, x1. So x1, the coefficient of x1 is -4. Then you say -4 divided by 2, which is -2. And then the second one is 2 divided by 2, which is 1. You achieved that. Then this following one is -7 over 2. Next one is 1 over 2. Then the next one is 0. The last one is 2, because it's 4 over 2. According to this algorithm here, x2, r2 tend to this. So you start by filling that one because it's simple. Then you are moving on to the next one. You choose now. It's either r1 row 1 or r3 row 3. So the simplest one actually is r1, because r1, therefore if you simplify that, it's going to tend to r1 plus 2r2. So to do that, remember that here you have your 4 times 2, which is going to be -8. So therefore it's 4, then minus 2 times 4, which is 4 minus 8. So 4 minus 8, you get -4. So this 2 is going to lead you to -4. Then you do the very same thing to the rest. So if you continue with this algorithm here, you are going to get 0. You're going to get 0 here. And then for the next one, you're going to get -5. Next one, you're going to get 2, 0. And then your b, since you are going to say the b, remember that you're using this one here, which is r1. R1 is 0 plus 2 r2, which is plus 2, which is 8. Then here is going to be 8. Using this algorithm here, this one, the first one, to fill the first row. So to fill the next row, we are going to use this, which is the last row, row 3. So row 3, we're going to say for the first one, remember that row 3, if we simplify that, it's going to be row 3 plus 5 over 2 row 1, row 2. So row 3, for the first time, it's -8. So -8 plus 5 over 2 into row 2 is -4. So that will give you -18. And then you do the very same thing for the rest. Then for next one, you're going to get 0. This one here, you're going to get 55 over 2. It's -55 over 2, and then you get 5 over 2, you get 1, then the last one is 13. Then that's your new table. So you're done with this equation after completing the table. So this is how we complete the table. Then let's move on to the next question. So this is, consider the following linear programming problem. Max z is equals to minus 3x3 subject to minus 8x1 minus 2x2 minus 2x3 is less than or equals to 9. 6x1 minus 5x2 minus 8x3 is greater than or equals to 4. Determine the initial table in the canonical form. So remember that you have to, here it's unlike the last one. Here you have to write the problem first in a standard form, and then after that write the problem in a canonical form as they said here. So the first thing to do is to convert the problem to a standard form. So to do that, just say max z is equals to minus 3x3, then subject to minus 8x1 minus 2x2 minus 2x3. So remember this, since it's less than or equals to, so that means you have to add something, add the slack variable. So add the slack variable, which is s1, or let's call that actually x4. Add x4 for this to be equals to 9. Then the next thing to do, take the second constraint, 6x1 minus 5x2 minus 8x3, and then subtract x5, which is a surplus variable, because this says is greater than. So if it's greater than, I have to subtract something, is equals to 4. Then after that, write the problem in a canonical form. The problem now it's in a standard form, but not yet in a canonical form. I will explain why. So here you have to say x1, x2, again x3, x4, x5 are all greater than or equals to 0. You restrict your variables. So after that, the reason I'm saying this problem is not yet in a canonical form, because if the problem is in a canonical form, you must have one variable in each constraint that has a coefficient of 1 on that constraint, of positive 1 actually, and then the coefficient of 0 in other constraints. So here we have only one constraint that it's in such form, which is x4. x4 has a coefficient of 1 here, and then 0 here, and then 0 there on the objective function. So x1 is the only constraint that satisfies that condition. x5 doesn't, because it's minus 1. So that means we have to add something. So here we're going to add what's called artificial variable. Artificial variable. So we're going to add artificial variable. So artificial variable is represented by the letter R. So you can rewrite the problem if you like, but now I'm going to just rewrite the second constraint just to change it to a canonical form. So the second constraint is going to be 6x1 minus 5x2 minus 8x3 minus x5, then add one variable is r1. So it is called the artificial variable, is equals to 4. So you are adding this variable so that you can convert this problem to a canonical form, because now you're going to have one variable that has a coefficient of 1 on this constraint, and then the coefficient of 0 on the rest of the constraints. So that means your problem now it's in a canonical form. But we consider this one. So as I said, you can rewrite the problem if you like, but here I'm just going to rewrite the second one to save time. So after that, you have to decide which variables are the basic variables and then which variables are the non-basic variable. And then remember, after adding this R1 here on your max, you have to add R1, you have to subtract, so you subtract for the maximization problem and then you add for minimization problem. You subtract R1 multiplied by M. M is the biggest number in the problem. So R1 here, we assume that R1 is 0. So that means it has no effect on this 4 here, R1. So you subtract R1 and M on the second problem not in a standard form, in a canonical form. In a standard form, you don't subtract this because initially you had this one. Then on a canonical form, it's where you go back and say subtract for maximization problem and then add for minimization problem. So after doing that, now you have to decide which variables are your basic variables and then which one are the non-basic variables. So a basic variable is a variable that has a coefficient of 1 on one constraint and then the coefficient of 0s on the other constraint, including the objective function. So we have x4. x4 has a coefficient of 1 on the first constraint, 0 on the second, 0 on the objective. We have R1. R1 is one of those constraints, of those variables that has a coefficient of 1 on one constraint, which is the second constraint, and then 0 on the rest of the constraint, including the objective function. So these two things are the basic variables. Then the rest are the non-basic variables. So what you shall write here, for the first one is x4, the last one is R1. When you fill, because this space here, it's for basic variables. Then after that, remember that here on this space here, you write the coefficient of the objective function. So the coefficient of the objective function there, we have for the x1 on the objective function here. Remember that x1 initial were not given, so it's 0. So we're going to write 0. And then for the x2 were not given initially, so it's 0. x3 were given, it's positive, but we're going to write positive. It's negative, we're going to write positive, because when you take it to the other side, it becomes positive. x4 initially is not there, it's a variable we just added, 0. x5 is 0, but R1, remember that after converting, they said determine the initial table in a canonical form. So in a canonical form, you have this max here. So the value of the R1, remember that this is minus R1M. So if you take this to the other side, it's going to be positive. So the coefficient of R1 is M. So the problem initially is equals to 0. Then you come to the first constraint. It's here. So since this constraint it's already in a canonical form and then standard form, that's why we didn't write it in a canonical form. So it's going to be minus 8, then minus 2, then minus 2, then 1, then 0 is equals to 9. Now 0 here, 0 also here is equals to 9. So the last one is here, is this one here, the one in a canonical form. Be careful, don't take the one that is in a standard form. Take this one because they said you have to write the problem in a canonical form. So it's going to be 6, taking it from here, and then minus 5, minus 8, minus 1, 0, sorry. Oh, This one is 0 here. X4 is 0. X4 is not there, 0. X5 is -1. R1 is 1. Then B it's 4. Then you're done. Then this is the end of the question paper. See you next time.